Hello and welcome to Lecture 8 of Chemistry for the Interdisciplinary Sciences. Today we're going to be talking about metallic bonding and metals. So let's have a quick look at the learning outcomes. So by the end of this lecture I'd like you to be able to draw and describe metallic bonding and also describe the factors that affect the strength of metallic bonding. We're going to have a look at solid deformation, especially crystalline solid deformation, and we're going to have a think about how exactly deformation happens in the physical world. We're going to talk about alloying and how you can change the nature of a solid, especially a crystalline solid, to avoid deformation and to change its properties. And finally, we're going to have a look at crystalline structures and how that's useful to us in the long run. There is a large section at the end of this lecture which is about crystallography that is not examinable. I'm using it to show you an example of how crystals and lattices especially are used in the real world. So let's get started. In material science, we're looking at this sort of thing really. We're thinking about physically how do the atoms pack together and what does that mean for the properties of the substance that comes after it. And a lot of the times as chemists we're trying to design substances, we're trying to design their properties. And so we need to have a really good idea of what one thing does to affect the other, if you want. So I just want you to start by thinking about this question. If you were going to replace drinking bottles and window frames, aeroplane wings, what materials would you make them out of? And you might choose the ones that are already chosen, but just take a second to do that and pause and have a think. And I want you to think, why have you chosen those materials? Okay, so you might have had a few different thoughts about each one. Let's say the drinking bottle, for instance. With the drinking bottle, you might have said plastic, and that might be because you prioritise things like lightweight. For your plastic bottle, you don't want it to have too much to carry. You don't want it made perhaps of glass because that's going to be fragile. The plastic can avoid, squeezing and so on. It's pretty robust. It's quite unreactive. It's pretty reasonable. You might not make a drinking bottle out of iron or something like that because it would rust, or even worse, something like lead. So the Romans especially like to use lead for water storage, but they also like to use silver for water storage. So lead seeps into the water and it slowly kills you. But silver has some weird antibacterial properties that we don't completely understand yet. So there's kind of two sides of the coin there. Again, worth doing if you're thinking about long-term storage, then maybe a silver bottle does make more sense. Perhaps glass bottles do make sense if you're going to partner them with some other properties. So I think, like, for instance, a vacuum flask, a thermos flask, that we usually would say, normal humans, that can withstand the vacuum, the pressures caused by the vacuum that is under it, and so making it out of glass makes sense. With a window frame, you might think of wood. Wood's great, except for that you have to sand it and revarnish it every couple of years. It's a real pain to own wooden windows. They swell and shrink dependent on the moisture in the atmosphere, so that's kind of suboptimal. But on the other hand, they do degrade, and if we're starting to think about what happens to objects after we have used them, then wood makes more sense than something that actually is used, like PVC or something like that. So PVC is polyvinyl chloride. It's a polymer, and we're going to see polymers later on in this course. But it's a really good material because it's very, very inert. It would rather bond to itself than anything else. And so it is very strong. It's very water resistant. It doesn't want to absorb any water at all. And it's, a little bit flexible. So should there be some movement in that, it can handle just a little bit of flexible change. Unlike something like wood, for instance, which might splinter and fracture. Aeroplane wings, you clearly want it to be made out of something very, very strong. But you also want it to be made out of something very, very light. And the combination of those two properties are very seldom, in the Venn diagram, there's a very small overlap. So you might think about things like carbon fibre, for instance, which is very, very strong. It's got good tensile strength because it's got lots and lots of strands there in lots of different directions, all holding and resisting movement in any direction. So something like that works. Aluminium works pretty nicely. It's a very light metal but quite strong. Titanium is a nice strong light metal. But nonetheless, a metal is a metal. It's quite dense as it goes, whereas carbon fibre is a lot less dense than that. So we have to think about the properties of our materials, both in terms of how it's going to handle stress and strain and how it's going to perform its function while there are forces acting upon it, but then also how is it going to avoid chemical change? How will it avoid being weathered, for instance, reacting with oxygen, or seeping into water and affecting the thing that it's actually used for? So materials, we have to think about this quite a lot. Now, so far we've looked at bonding between atoms that want to give up electrons and an atom that wants to take an electron. That was ionic bonding. Last few lectures we've been looking at covalent compounds where atoms both want to gain electrons. Now we're going to look at when you have atoms that all want to lose electrons, and remember that those are metals. So today we're having a look at metallic bonding. Generally, these contain only metals, though of course we're about to look at some non-metal substituents in the alloys, but things that are metallically bonded tend to conduct electricity, and this can be things like brass, for instance, which is an alloy of copper and zinc, or bronze, copper and tin. You've got, your coins and all of those things, and then pure metals like aluminium, mercury, for instance. All of these things are metals, and mercury, even though it's a liquid, does conduct electricity. Now, the reason that it conducts electricity is because of the nature of metallic bonding itself. Because all of the atoms want to give up electrons, what happens is they do it. They all give up electrons into a sea of electrons in between them. So what happens is the metals give up those electrons to nearby atoms, which then give them up, and so on. So this means that we end up with the electrons just sort of floating about and unable to attach directly to a specific atom. Why? Because none of the atoms want them. None of the atoms want any electrons. So we're thinking about lithium or sodium or something like that. They are a couple of electrons away from having a full electronic configuration as long as they lose them. And in losing them, they come to that lovely full shell configuration with a positive charge at the end of it. So our metals are positively charged ions in a sea of delocalized electrons. And this is what makes the substance conduct electricity. It's by having those free-flowing electrons, where if you supply some electrons on one end, it will push electrons along all the way through the structure and then push electrons out at the end as well. So having those delocalized just means having no specific place to be. If you want, they can move throughout the whole structure. You get this amazing property of conductivity, which we are using right now. I'm using it to transmit this video to you, for instance. Now, you can imagine that generally this is going to be quite strong then. The things that are going to affect the strength of this, let's have a quick think about that. So I just want you to pause and have a think. What's going to affect the strength of the metallic bonding, do we think? Okay, so you might have come up with the first one, which is similar to the ones that we saw with ionic bonding, which is packing efficiency. How closely do all the ions pack together? They're all going to be the same size, would you imagine? So we're going to get some close packing here, and we'll talk about that in a second. So that's going to affect it. The other thing that's going to affect it is how many electrons do these atoms want to give up? So I mentioned that aluminium was quite strong. If we have a quick look at the periodic table, we see aluminium there in the 3p1 position, proton number 13. It wants to give up 3 electrons in order to become to have the same electronic configuration as neon. Giving up 3 electrons means that in the metallic bonding, in this, every cation, which is going to be a 3+ cation, is going to have 3 electrons in the delocalized cloud, and those negative electrons is what's holding all the cations together. So the more electrons given up by the metal, the stronger the metal will tend to be. Does that make sense when it comes to titanium, which is the other one that I mentioned? Yeah, titanium's in the top row there, the D block. It's in the 3d2 position, which means that it can either give up 2 or 4 electrons, and when it gives up 4 electrons, again, that metallic bonding is very, very strong in between the two. Again, because there's just more electrons between higher positively charged cations there. Now, the problem with having these structures is, if we have a quick look at the image that's behind me, a pure metal tends to pack together in a regular structure. Now, at the moment, these atoms are not very efficiently packed. They're just in a array that is regular, and that's all I want you to imagine for now. You can imagine that if I go, which way can I do it? If we started to push on this top row of atoms, so if I were to physically push them, what would happen is the top row would start to move over. They would slide, because now the atoms aren't attached to each other. They're just all attracted to sort of the glue in between them. But that glue never sets. It's always moving. It's delocalized. So what we find is that if we apply stress to something, so for instance, look here, I've got a paper clip. If I take my paper clip and I apply some stress, all of the atoms have moved because now it's locked into this new position. Being locked into this new position physically means all the atoms have to slid over each other, or in this case, they're cations, aren't they? With that negatively charged electrons all around it. They move. Now, that can be a good thing. In this case, the paperclip, I might want to rearrange it into something new and something different. But I might not. So I might have something like iron, for instance, where I want to make it a little bit stronger and turn it into steel. So I don't have a spoon here, what a shock. But if you've got things like cutlery, for instance, that's iron with just a little bit of carbon in it. And this is where we become talking about alloys. Now, an alloy is where you have a metal with another element substituted in. It's usually a metal, but not necessarily. And as I mentioned with steel, it's carbon. So when you do that, you either add in an atom that is approximately the same size as the original metal atoms, or ions in this case, or it's significantly smaller or significantly larger. And this is where we have two different types of alloy then. We have our substitutional alloy. That is where the new element has simply replaced the old element atoms in that lattice. Or we can have an interstitial alloy. That is where the elements atoms are hanging out in between the layers there. Now, neither of these is better or worse than the other. They do have very slightly different properties. You can imagine with the substitutional alloy that the layer is now not the same thickness all the way across. So if you look at the top layer, for instance, it has that layer, but then it has that little dint in it where the new element is, that's slightly thinner. And those little dints, those little ridges, make the layers a little bit harder to move over each other, because now the shape's not regular and it can't just slide and skate over the other one. With the interstitial alloys, we get something very similar going on. The atoms getting in between the layers, again, lock those layers from sliding. Now, here's the thing, though. With this pure metal here, again, I think it's probably just a steel paperclip. If I bend it, it bends. And quite often, in structural terms, that's useful to some degree. What you do not want is what would happen with a strong interstitial alloy, which is that if I bend this, it will not change for a long, long time, and then eventually it'll fail, and the whole lattice will just split apart. So let's just draw. So it'd be something like that. It would catastrophically fail. The two sections would not be attached to each other at all, and then it full-on fractures. And we call that sort of substance a brittle substance. So this is a malleable substance, a substance I can change the shape of. And if I had something like, well, for instance, my baton, my conductor's baton, if I bend it, it will resist that bending for quite a long time, and then it will snap. And again, that can be useful. If it can hold a lot more pressure when it's being bent than it could otherwise, then that might be worth it. However, if you are using it in an application where you need a little bit of flexibility, then clearly that's not the best alloy for you. Now, what I don't need you to do is be able to decide what type of alloy you want, but I do want you to be able to describe how deformation, changing shape, involves layers of these ions moving over each other. And if you want to block that deformation, if you want to stop it from being so malleable, then you're going to add some extra atoms. So, what I'm going to do is show you a little demo now that I started a little while ago. So what I've done is I'm going to try and put some gallium atoms into a can. So I got myself an aluminium can. This is a steel can, which is not so helpful. But I got myself a can. I've got some gallium, and all I'm going to do is sort of pop it onto the top. So let's watch. So I'm recording this a little bit earlier. What I've got here is some gallium, which is, as you can hear, it's a solid metal as it is. However, it has an unusual property in that its metallic bonding is not really all that strong, which means that I'm going to be able to melt it with just a little bit of heat here. So all I've got is a can of hot water inside this beaker, and I will give it a prod with this paper clip. Okay, I don't know if you can already see that, but can you see there's a liquid front sort of moving along the gallium surface there on its own? So now, can you see that it's started to melt? And there we go. So it didn't take very much energy at all to get this metal to become a liquid. And in fact, this is how, you know, magicians, when they do the trick with the spoon, where they rub the spoon and then it falls apart. This is what they do. They put a linker of gallium in there and then they just use their body heat to melt it. And it would be enough for me to do it in my hands. It just wouldn't have been very quick. The reason it's a bit messy at the moment is because I already tried with this gallium on a steel can and it doesn't work for reasons that I'll talk about probably later on in the lecture. But what I'm now going to do is introduce this gallium to an aluminium can. So I'm just going to clean off this paper clip. Hopefully I've got rid of most of the scum there. The scum is just going to be gallium oxide, essentially. So I'm going to take this aluminium can, and it's important that this one's aluminium because that means it's a pure element. So it has a rigid crystal structure that's really repeating. Remember this business here. Really repeatable. With the steel can, it's got those interstitial elements there getting in the way, really, of the gallium absorbing through. So what I'm going to do is pop the gallium on, and this is why it's in a can in a cup, so that I can empty that out. Please stay tuned for my series of ASMR experimental videos. Okay, now I'm going to pour the gallium onto the aluminium can, ideally not down the hole. Lovely. I'll leave that for future me to sort out. And then here, with the gallium on the can, what I'm going to do is scratch the surface. Now, the reason for this is that the aluminium has an oxide layer. So I'm just using this to scratch through that layer and expose the pure aluminium to the gallium. And then I'm going to just leave it there for a few hours and see how it goes. So, next time you see me, it'll be in the future. Great, so we've had that going for a little while, and we're basically looking at the aluminium can being like the pure metal behind me. So there we've got the regular structure of the aluminium atoms, and what the gallium's going to do is slowly get between those layers and start basically either substituting or being interstitial in the original lattice. Now, you can imagine that what that means is that the lattice is going to have to move out of the way of the gallium atoms to allow them in. So let's have a look at what that looks like when that happens. So 5 minutes after that last video, here's what we saw. Okay, so I've moved the camera very slightly closer and obviously in the frame here, so that we can start to have a look at this gallium on here. Now, it's been about 5 minutes, if even that. And can you start to see that there's a crack here forming already? And can you also see that the gallium seems to have changed in colour? Here we've got a bit of a scum on top again. So I'm going to pause again and we'll update in a couple of hours. So then what I thought I'd do, because it looked a little bit interesting, you can see that already there's starting to be fractures in there, that the lattice is moving out of the way, really, of the gallium atoms. I thought what I'd do then is try a little bit of a time lapse. So here we're going to watch a video where I've popped some aluminium on a different can, and essentially I just left it. Now, what speed is this going? Every second is about 10 seconds here, but can you see already we're starting to see a little fracture in the can over here? So this is the gallium now pushing into the lattice, and it's it's even spurting out of the other end. Can you see that? And so the can is deforming because the layers of the metal are having to move out of the way of the gallium atoms coming in. Cool. So it has really separated. Now, let's have a quick look at it then. So let's pop over to here. Let's have a look at the can now. So I turn it around. So can you see that, first of all, we've got a full-on fracture over here. Now, it has kind of got to the consistency of cardboard. So if I just pull on it a little bit, like that. Okay. So, I'm going to try and get this in a sensible position. So can you see how this is just now fracturing off the aluminium? It's not sharp, and in fact I can start to separate out the layers. Don't know if you can quite see that. So if I take this and I just pull it, all that I'm doing is applying a tiny bit of force. And you can see that the can is just falling apart. It's just like cardboard here. So we've got significant weakening here of the metal lattice, simply just by adding that interstitial gallium atom. So I'm recording this a little bit earlier. What I've got here, okay, so sorry, those gallium atoms there have really messed with the structure of the lattice, such that it no longer has the same physical properties it had before. It's now a lot easier to break apart. It's not at all crinkly. So hopefully you can see all of that. It's been very easy. Now, this is why for a long time mercury thermometers were banned, and well, I say a long time, they still are, banned from aeroplanes. It's because aeroplanes are made with aluminium a lot of the time. Nowadays that we're obviously using more advanced alloys, but aluminium used to be especially the honeycomb floor of the aeroplane, and you can imagine if a little bit of mercury got involved, the fact that gallium was a liquid is what let it move through the lattice there, because the ions were free to sort of move about and find a slot that they could go into. Just going to clean my hands of all that delicious gallium. Okay, so hopefully that's given you an idea of how solids deform. It's by movement of these layers of atoms over one another. And we can try and avoid that deformation if we want to, using alloying by adding another element. You can see that here that alloying hasn't been successful in helping it, so we do have to be really careful in what we're doing and trying to design specific materials for these uses. So let's have a look at some other crystal structures, because we've mentioned already ionic compounds can form lattices, so we've seen that repeat, well, basically this, haven't we? Plus, and all of these are negatively charged, being attracted to that central ball there. We also mentioned that covalent compounds can do the same. So I mentioned in the last lecture that carbon tends to also form these giant covalent lattices. So let's have a quick look what that looks like. Here we have the carbon atoms, especially let's look at this one in the middle here. So that one has 4 different carbons attached to it. And basically every single carbon looks the same for that. This is what makes diamonds so hard then. It has really strong bonds in between every atom, because those are covalent bonds, not metallic or ionic like the ones we've seen so far. And it's a very regular structure. So if you fracture it in some way, you're going to have to break the whole plane of covalent bonds, and that makes it very, very strong. In fact, diamond's one of the strongest compounds on Earth. I think it might be the strongest, in fact. We also have things like this, glass. Glass is a covalent compound too. It's made of silicon and oxygen. It's silica dioxide, and so you've probably heard that glass comes from sand. That's basically correct. There's a slight change in the composition, but that's all that's happening. And that too is a giant covalent structure. Now, the one I've included in the slide here looks quite regular, doesn't it? But in fact, the definition of a glass is that it does not have a repeating crystal structure, and instead is very deformed and amorphous in there. So it's not always the case that long-range order is what conveys strength to it, but part of the reason that glass is so brittle and fractures so easily is because of the disorder inside its system. It still has the same strength as bonds as diamonds does, but it does not have the regularity of it that means that when it fractures, it can sort of fracture in any place because it doesn't have to find a plane to fracture down. When I say a plane, I mean, for instance, all of those atoms need to detach, or all of those atoms need to detach. There. Now, whenever we have molecules like this, we tend to find that we've got these really interesting properties that are conveyed through by nature of it being a solid. So the fact that it's a solid is what makes glass and aluminium so strong, because the atoms are physically bonding together. And again, in a solid, it tends to be quite regular. So let's go back to these questions then. What would you make the following objects out of? Well, in this case, what we've got then is we've seen that perhaps we're going to start thinking about some alloys. Sorry, I'll just mess with that. There we go. So, for a drinking bottle, okay, well, we can maybe start thinking about steel as a really nice substitute. Steel is much less reactive than iron on its own. The carbon being in there changes the electronic properties of the iron atoms, and so that might be something that's useful to us. A window frame, okay, we might still think about plastics, but perhaps we're also going to think about, again, alloys like steel. Steel was a real game changer there. And for our aeroplane wings, we're going to get way more advanced than just having pure aluminium or pure titanium. There are lots and lots of alloys now that have even stronger metallic bonding with a reduced movement of the layers over there, and therefore reduced deformation, but also are less dense and so are lighter, which means you have to pay less to use the fuel to move it around, really. So again, there are lots of answers to these. There's no correct answer. I just want you to understand that there are lots of different ways to use our materials, and we can start to design materials to find out if we can make it stronger. So again, this alloy was weaker, but perhaps there are some alloys where if I get atoms that are closer in size to aluminium, that will actually improve its tensile properties in there. Okay. So this takes us to the idea of crystals then. So we've already seen this, and we saw crystals before with the ionic compounds in there. But I just thought I'd show you a few more interesting crystals. So we've seen these salt crystals up over here. Sorry, I'll just get rid of my pointer. We've seen these salt crystals before, but see, look how nice and cuboidal they are. That is to do with the fact that it basically packs like this. A chlorine and then sodiums all the way around the outside. But I mentioned that some crystals have different structures. So up here what we've got is a dodecahedron. So again, my D&D friends, I'm thinking about a lovely D8 dice. So that sort of shape, we can get this sort of shape from a rock, essentially. So that crystal will have actually grown in that shape, and the reason it grows in that shape is to do with the way that the atoms pack together. Directly behind me, I've got some hexagonal crystals there, so you see how they've got that hexagon shape. Again, that usually is conferred by having triangular-shaped molecules all coming together to make that hexagon shape, and it amplifies out into the larger structure. Here we've got a whole load of crystals whose faces have aligned, so it's created what we call needle crystals. So we've got those needles, and the face of each needle has actually started the next crystal growing, and then the face of that one has started the next crystal growing. Notice that it doesn't look like we've got crystals stacked on top of each other end to end. We've only got crystals stacked on top of each other side to side. That suggests to us that there is one face of the crystal that can activate the rest of the molecules to order themselves into the right shape to make a brand new crystal. And so when you're doing crystallization, that's what's happening. You've got to have the molecules ordering. We're going to have another look at that in a second. Finally, what we've got over here is pyrite. So you probably know pyrite. You might have bought some fool's gold when you're a little bit younger. Pyrite is a really beautiful compound. And here what we've got is what we call twins. Now in this case we've got triplets, in fact. 3 separate crystals which have all grown into each other. These are natural. They're not cut into this shape. This is found in a rock when you dig it up. those have all grown into each other and created what we call a twin crystal. And as I say, this one's got 3, so we might call it a triplet. That really gets in the way of figuring out what the compound is. But you can see how beautiful they look. And again, they've got this lovely cubic shape there that is a result of the fact that the atoms are bonded like this. And that structure gets repeated over and over and over again, but it still comes out in the overall shape of the crystal. So we already had a look at ionic solids. Let's take a quick look now at our non-ionic solids. So let's say now we're talking about metals all on their own. So if we provide a little bit of temperature, this is what would happen. So when these things are dug out of the earth, what's essentially happened is they've dissolved into the magma in some way. They've been, provided by meteorite maybe, or otherwise they're just dissolved in the magma. And as it cools and creates the Earth's crust, we reduce the speed of those molecules, if you want. And as they reduce down, they sort of start to grab hold of each other. You see how we got little regions now where they're all sort of coming together. Now, if the Earth, the crust, the new crust that was being formed at the time that these crystals formed, cools very slowly, what we tend to create is one single lattice like that. And I think I might have shown you this already with the ionic compounds. The slower you grow your crystals, the bigger they get. And so that's how we were likely to have found the last few crystals, the lovely dodecahedron one and the 3 cubes one as well. And we also saw what happens when you cool it slowly. So now you can see we've got these separate crystallographic domains growing, and then they're all attaching together. This is how that little triplet must have grown. We had them cooling way a little bit too fast, and they started sort of attaching to each other, but still growing together. And notice we've got this over here that's doing nothing. So that might eventually become a passenger in there. So when you're growing yourself a crystal, what you want to do is do it as slowly as possible. Now, can you see in this crystal we've got a slight deformation, which is this hole here in the middle. That would also cause us a problem in assigning what's going on in the crystals. But see how the structure still seems to be very regular around it nonetheless. And so again, this crystal structure is basically determined by how strongly attracted the atoms are together. And when they were ionic, we saw that it forced itself into a very regular structure in there. So our crystals grow, and once we've got our crystals, then what we can do is start to think about, well, what is the actual shape? And so now we're into the point where you don't have to understand everything that's coming after it. I'm talking about it because it explains how we use crystallography and why it's important. And also, you're studying at Leeds, and we kind of invented this. The Braggs were a father and son science team, which doesn't happen now so much, but they won the Nobel Prize for crystallography, and that's what we're going to talk about. If they're at Leeds, we might as well talk about them. So I mentioned this idea that before, the slide that we had before, which would go all the way back there, this metal, these atoms are actually not packed as efficiently as they could be. If we displace every other layer, we can get them packed a lot closer, and that is close packing. So let's imagine we have all of these oranges, for instance. With these oranges here, we've put the orange in the little sort of triangular gap in between the oranges below. We can start thinking about the packing. So I might say that there's a layer that I'm going to call A, and that's just got a certain spatial location. And if I put the next layer in all of the little holes there, then I might call that layer B. And then I can choose to either put the remaining ones in. You see how there's a little hole left on top of both of these atoms here, both of these layers. That hole hasn't got anything on it, so I can pop another layer on there, or I can carry on the pattern that I had before and pop my layer back in this hole here, so I can put the next one in there. Oops. So there we go, we got the atoms laid directly on top. So let's have a quick look at this one. If we look at the oranges here, have we got an A, B, C or A, B, A layers? Well, the first layer is there, but notice that the top layer, so let's say that that's the B layer, we'll call that the A layer, B, and then at the top we've got C. it looks like layer C is directly on top of the orange in the middle, isn't it, of layer A. So in fact, that must be another A layer. So here we've got A, B, A layers. Again, this is not examinable. I'm just mentioning it because it changes the nature of the structure of the compound and therefore the shape of the crystal. Just having those slightly differences in the packing, which again is caused by the way that the atoms interact with each other, is going to change the nature of the crystal that comes out at the end. So, in 1895, Roentgen invented the X-ray, which is an interesting thing to do. And the very first thing that he did was he asked his wife, "Can you just pop your hand in this X-ray for me, please?" And so that's what we've got an image of there, X-rays. Crystallography works using X-rays. X-rays are basically just very high energy photons. It's like visible light, but with an even smaller wavelength there. And because their wavelength is so small, it can be affected by electrons in a structure. So Roentgen invents these X-rays. He can't figure out if they're light. Einstein says that they are, and that's basically it. There's a whole load of hoo-ha. But essentially, we eventually can use those X-rays to find out about the simple ionic compounds that we were looking at before. So we looked at these in the ionic compound lecture, but please do go and have a look at those. Definitely click on this image and have a go at manipulating the structure yourself. That was a very difficult thing to solve, and that's something that the Bragg solved to get their Nobel Prize. But we've come on a bit since then, so I just thought I'd show you how it works. The way that we can figure out what the structure of a compound is, because that's what we're doing there. We're physically taking pictures of molecules, essentially. It's a mathematical picture, but it's a picture nonetheless. So what we do is we mount our crystal on here, on the tip of this, usually a piece of glass. And again, the reason that it's glass is because it's not very regular, unlike the compound that we're going to look at. And so it's not going to have any meaningful, constant movement of the photons in this case. So this is the X-ray source, this sort of pencil thing, and it's going to shoot an X-ray through our crystal. So we've got to be really careful to mount our crystal onto there. So there we go. Then we got the detector. So the X-ray is shot through the crystals and it's detected and it creates a 2D image. So just basically like a photograph of there to try and see what light is coming through that crystal. We have the goniometer. Its job is to move the crystal around in 3 different circles. So it can turn around on its base there. It can turn that arm around, and finally it can turn the crystal around as well. So having all those different movements means that I can turn this crystal in all directions. Now I mentioned before that we're taking 2D images of the X-rays coming through. But what we then do is we turn the crystal half a degree and we take another image, and then we turn the crystal half a degree and take another image. And we look at how that image changes as we move that crystal around. That means that rotation, we can sort of use that as a third dimension. We've already got a 2D image, but now we've got a third dimension that we can start to change. Here we have the cryostream. The cryostream is basically just a very cold tube of cold nitrogen. And when I say cold, I mean minus 100. Around there is pretty good. Minus 100 degrees Celsius. And the way that we make that is basically by putting liquid nitrogen into a tank and then slowly injecting it into the cryostream so that it breathes that cold air over the crystal. Why do you think that's important? Well, if we pop back to the this thing here, if we got that crystal sort of being normal room temperature, it might look a little bit like this. So we got some motion there of the atoms, and that's what heat is. So when something's hot, the molecules are physically moving around or vibrating a lot. Because this is solid, they can only vibrate. If this was a liquid, then they'd just be whizzing around all over the place. And so if we just cool that down with the goniometer, with the cryostream, then we stop moving those atoms, and it makes it much easier for us to take measurements on them. Okay, so we got the microscope camera. That lets us look at whether the crystal is exactly in the middle of the X-ray beam. And then we've also got, I think, the beam stop. Yeah, so that is the bit that basically stops the X-ray from being shot directly into the camera at the other side here, which would immediately damage it. So what we're going to see in the images that we look at is a sort of shadow of the beam stop in there. And it doesn't matter that we don't have that data because that is X-ray going through the crystal and not interacting at all with it in any way. So we're not really all that worried about it. We have the beam stop there to protect the camera. So that's what it looks like through the microscope lens. And I told you that I'd grown little hexagonal crystals. So here's one of my little hexagons. You can see that it's got some little passengers up here at the top that we don't like. But still, you got this nice hexagonal crystal. You pop it into the middle of the crosshairs there, and then you just make sure it's in the middle of the crosshairs as it goes through all three of its circles. And then you take your measurements. So the X-ray goes through the crystals, and as it goes through electron densities, it goes through those orbitals that we've been talking about all this course, it interacts with that change in density, basically with those electrons being around, it interacts, and the angle of that light changes. It's like a diffraction. So, you know, you've seen the old, you put a pen in a beaker of water and it changes angle. The same sort of thing is happening with the X-rays through the density of the electrons. They also get moved in there, and that's diffraction, and it's refraction when it's in the water there. So they get moved, they get their angle changed in 3 dimensions, and so we then take an image of it, and that's what it looks like. So there you can see the shadow of the beam stop. We've got all these little spots. Now, why spots? That's weird, because it's suggesting that the crystal doesn't diffuse the light, you know, like a lens where it just spreads out all of the rays completely uniformly. What it does is it spreads out some of the rays in some direction, further and further away from the crystal itself. And you can see that we've got bright spots all the way out here. So just think about the change of the angle that must have happened to make an X-ray appear all the way over there. That can only happen when there's something called constructive interference. So I'm not going to go too far through this, but all I'm basically saying is that the extra distance that one of the beams has to travel compared to the other has to be a full wavelength difference. So you see how here we've got a whole trough, a whole peak and a whole trough, a whole peak and a whole trough. That means that the waves can come together and be constructive. So when they're constructive, it just means that they're both going up and down at the same time, in the same frequency, let's say. When we've got destructive interference, it means that they are opposite in their phases. And so if you were to plot the average distance of my hands here in front of my face, you'd see that they always stay at 0. Whereas here, with constructive interference, you can see that they always are going in that cycle of up and down. And when they add together, that gives us the bright spots. So there are only some very specific beams that we do see in interacting with the electrons. Don't worry about all that. If you're a physicist, this is Bragg's law, and it's really useful, and Emma will be talking about it, I'm sure, at some point. So there it goes through the crystal, it gets detected, and as I mentioned, we have a 2D image, and we have a third dimension of rotation, and all the computer then does is essentially looks for all of the possible different refractions that it can. So we move the detector around the space, and what we end up with is a 3D map of electron density, because the electrons is what has caused the change in that angle. And so here what I've got is some structures from my thesis. So here we've got an aluminium compound with this strange motif attached, but you can just think of it as like a little 2-part biter. So it's biting onto that metal there. But this is, and these 3 images are, physically mathematical pictures of the molecules that I made. I know exactly what the shape is because this is a result of it. I didn't have to do any modelling or anything like that. I did have to tell it, oh, I think that's an aluminium and I think that's an oxygen, so tell me what the shape will look like. But otherwise, this is physically a picture of a molecule that I made in a lab on my own. And that is mind-blowing. That is something that's really useful to us as scientists, because we've been talking about how we'll use covalent bonding to make specific shapes and pop it into certain compounds. So, for instance, if you wanted to make a brand new drug, you might use in silico drug design. So what I mean by that is we find the crystal structure of a protein that you want to target. Let's say you know that you want to try and trigger insulin to be made, and that there's a protein in the pancreas that when it joins with a compound, it triggers the production of insulin. Well, all you have to do is tell the computer, look, here's the structure of the protein, which we would have got from crystallography. We would have used this whole process to get a physical, mathematical picture of the protein. And basically, I want you to design a compound that will fit into that little hole. And so that's what it'll do. And it's really useful to then be like, okay, cool. It suggests what the structure should be. And then some chemists will go off and make it and then test it and see if it is doing what it's supposed to. So this is how we make targeted drugs now. We're starting to think about, well, actually, how does that mechanism work in the body? And then can we trip it ourselves with our own drugs? And that's the game. You can also use lattice structures to actually create pockets that compounds that you don't know the structure of can sit in. So it's quite difficult to grow a crystal in the first place. The crystals that I grew of the aluminium, they grew over 8 months at minus 70 degrees Celsius. So they're very difficult to grow. And also they set fire in air, which was not great. So it makes it very difficult. You can even use these lattice structures to start basically making little pockets. So you have this compound, for instance. It's a few rings all fused together, and then those rings fused together, and then those rings fused together to make this sort of honeycomb lattice. And what's going to happen is your substance that you've made, so you've made something novel in the lab, you pop it into a solution that has this compound in it, and the molecules are going to settle into the most electronically and sterically, that just means shape, the best shaped space in the lattice itself, and you would expect that to be the same in every single pocket of the hexagon. Once you've got that, you've got a regular repeating structure, just like the crystals that we had before. And that regular repeating structure is what allows us to then figure out the structure of some molecules. So when they were doing this chemistry, what they did was they asked someone to try and figure out what the compounds were inside that structure. Now, this compound is famously difficult to get a crystal structure of. The reason for that is that there are no interesting atoms on the compound. It's all carbon and hydrogen. And usually carbon and hydrogen, hydrocarbons, my goodness. Hydrocarbons are things like petrol and candle wax, things like that. Not very regular structures, a liquid at room temperature for petrol, so that's just octane in there. This compound is very difficult to crystallize, but using this method of having the little hexagon pockets to sort of let it sit in its favourite place in there means that you end up with a regular repeating unit that you can find the structure of. And in fact, these researchers managed to find all sorts of different structures of compounds that are quite difficult to crystallize on the whole. And you can see how even the colour of the compound changed the nature of the crystals themselves. So here, each of these crystals is actually just that hexagonal lattice that we saw before, the honeycomb thing. But it's been changed in its colour by the compounds themselves. And look at this crazy compound over here. We got this crazy cube structure there. That must be very, very strained. All those angles around there are going to be 90 degrees. Remember we said when something had 4 bonding pairs, it wants to be 109. Here it's only 90, so it must be a really strained and difficult compound to get a structure of. Lovely. That basically takes me to the end of what I wanted to say. I just want to really quickly remind you about salts there. So remember that salts are where you've got your positive and negative ions in that lattice structure. I just want to talk about what it does with water before I start talking about dipoles properly. So I just want to say that when salts dissolve in water, the way it looks is like this. So I've got the sodium plus ion in there. I've got my oxygen atoms. They sort of hang around the ion and hold it inside a network of these water molecules there, and that's dissolution. So I'm just mentioning this so that you can imagine what it looks like when something dissolves. In this case, what you're going to see is the compound surrounded by the water molecules if we're dissolving salts in water, and I'm just going to skip to one more. And so that's what it looks like. When I talked about growing crystals, the best way to grow it is to dissolve the salt up into water, or to dissolve the substance up. It doesn't just have to be a salt. It could be like the hydrocarbon structure that we looked at a second ago. But you dissolve it up, and then you essentially cool it down to let them drop out. So I just wanted you to give you a sort of mental model of what the ions look like floating about in the water there. So I'm going to return to this when it actually makes sense, but I just want you to have an idea of how you might imagine substances dissolved in solvents there. Great. So I'll come back to this later. Thanks very much.